All right, clip number 3 for section 4 notes. To conclude our section 4 notes on inscribed angles and polygons. In the previous 2 clips, we talked about inscribed angles, simply an angle whose vertex is on the circle. In this clip, we're going to be talking about inscribed polygons, something a little bit more complex. Now we have a many-sided figure fully contained within a circle, but that term inscribed, again, has a different connotation there. An inscribed polygon, whether it's as simple as a triangle or as complex as, say, like a decagon, a 10-sided figure, in order to be inscribed, each of the corners, each of the vertices needs to be on the circle. So with an inscribed angle, it's a single vertex. It's a pretty simple thing that it has to do. It just has to be on the circle somewhere. All right. For an inscribed polygon, each of its corners need to be on the circle. So it is very possible to draw lots of different shapes where like none of the corners are on the circle, or one's outside, several are outside. There are lots of different ways. In order to have the special classification of an inscribed polygon, each of the corners need to be on the circle itself. And just to throw this term in here, it's been mentioned before in previous units on this kind of stuff. The term circumscribed, as opposed to inscribed. Circumscribed means that it's a shape it's the shape that's around the inscribed shape. So in each of these cases, the shape that's circumscribed is a circle. You'll recognize that prefix circum from circumference. It just simply means around. It refers to the shape that is around another. Inscribed simply means written on the inside of that shape, but specifically with corners on that shape. All right, so in this clip, we're only going to talk about, in this section, we're only going to talk about 2 of the polygons out there. There are obviously lots and lots more, infinite more, but we're only going to talk about the 2 simplest ones, triangles and quadrilaterals. And even with triangles, we're only going to talk about one specific triangle, and that's what you see here at the top, the inscribed right triangle theorem. So not only are we talking about a triangle, but we're specifically talking about a right triangle, meaning one of the 3 angles in that triangle needs to be 90 degrees. Okay? So the only way a right triangle can be inscribed on a circle where all 3 corners are on that circle is if one of those 3 sides, specifically the hypotenuse of that triangle, is a diameter of that circle. So formally it says in this specific diagram with this specific triangle, angle B is 90 degrees if and only if the hypotenuse, in this case AC, is a diameter of the circle. More generally speaking, the only way a right triangle can be inscribed in a circle is if its hypotenuse is a diameter. Now here's why. This is actually a direct reference to the inscribed angle theorem we talked about in the first clip. Inscribed angle theorem says this: an inscribed angle, like angle B right here, notice that both of its wedge points are on the circle as well, fundamentally creates an arc, in this case, arc AC. But notice that AC is a semicircle. It's half of the circle. Because AC is a diameter, arc AC is forced to be 180 degrees. Okay, well, according to the inscribed angle theorem, the inscribed angle needs to be exactly 1/2 of its intercepted arc. Well, if the intercepted arc here is 180 degrees, if I take a half of that, divided by 2, I get 90 degrees for that inscribed angle, forcing angle B here, in this case. They can be named whatever, but it forces this angle here to be 90 degrees. And vice versa would be true. If I had a 90-degree angle, what's going to be forced to happen is that the hypotenuse has to be the diameter. That's the only place it could be located. It couldn't be past the center of the circle because then fundamentally my arc would be less than 180 degrees. It can't be underneath the center of the circle because then my arc is bigger than 180 degrees. In either case, I'm fundamentally changing the measure of the inscribed angle. So the only way that that gets to exactly 90 is if the intercepted arc is exactly 180. And the only way that happens is if the chord that makes that arc is a diameter. So in short, The only way I can get a right triangle is if its hypotenuse is a diameter. It's kind of the punchline there. All right. Last theorem for section 4. Last theorem is the inscribed quadrilateral theorem. Inscribed quadrilateral theorem. So in this case, you'll be noticing very quickly the differences between these theorems. In one case, you got a triangle. In this case, you got a four-sided figure. So in your big ideas assignments and stuff, it'll be pretty obvious. But this one breaks down to a kind of a simple phrase too. And it's this green asterisk point right here. If I've got a four-sided figure inscribed in a circle, means all four corners are on the circle, then opposite angles or diagonal angles, or whatever you want to describe it as, opposite angles need to be supplementary. In this case, with these letters and stuff, that's going to force angle D and angle F to be supplementary. That means they add to make 180 degrees. Angle E and angle G will also have to add to make 180 degrees. There's a proof of this in the textbook. It's a combination of the inscribed angle theorem and the fact that within four-sided figures and all of the internal angles need to add to make 360 degrees. I'm not going to really go into depth with that, so let's just go ahead and take this at face value. If I've got a quadrilateral that's inscribed, all four corners of any, it doesn't have to be a square, it doesn't have to be a rectangle, as long as it has four sides and it's inscribed in a circle, all four corners on that circle, angles that are opposite each other or diagonal to each other, whichever you want to describe it as, opposite angles need to be supplementary. That means they add to make 180 degrees. Fairly simple computation there. We're going to see that in an example right now. All right. We're going to do two brief examples, and again, it should be pretty obvious which ones are which theorems we're going to be using in each case. But we're going to do these two examples. This is just representative of what you're going to see in your big ideas assignment and or on a test, hint, hint. So just be able to identify both. Again, one's a triangle, one's a four-sided figure. Pretty obvious which one's which. All right, so we're going to be seeing circles with polygons completely inscribed within those shapes. And in these cases, we're going to be solving for variables. I'm going to talk about different variations you might see in your assignment or on a test. In these cases, they're going to be pretty basic. It's just simple algebraic phrases, if anything at all, or just simply a variable in that location. But these could get as complex as having entire algebraic phrases like 3x plus 17 or 2x minus 90 as an angle measure. I'll talk about how that changes things, but essentially it's going to break down as combining like terms. Okay, let's work through these two examples. I'm going to jump to the whiteboard so I can zoom in on a bit and hopefully you can see the numbers in here. I know I've written them kind of small. Again, you can upload these off of Google Classroom so you can zoom in them as you will. Let's jump to the whiteboard. All right, part A. We're given the following circle. Name of the circle is circle Q, named after its center. And then we're given a diameter of that circle because it goes through the center. Wrong place. B and an A down here. So I have diameter AB. So before I do anything else, fundamentally, because this is going through the center, I know from an arc measurement perspective, this half is 180 degrees. I know this half is 180 degrees. The other thing to point out, I'm about to do point C over here to make to complete the triangle shape. It actually does not matter where on this half of the circle, or for the whole circle for that matter, it does not matter where C goes. Because of the inscribed angle theorem, because endpoints are at A and B, and this arc is 180 degrees, wherever I put point C, it's going to make a 90-degree angle. That's actually an interesting point right there. But we'll go ahead and put it here. It didn't matter really where it went. So we'll call that point C. So by drawing this, I will officially have created a right triangle. And so according to the inscribed right triangle theorem, this angle is forced to be 90 degrees automatically. Whatever is there, it's going to have to equal 90 degrees. And so in this problem, they give me the algebraic phrase of 2x. So you don't need to write this part. So I'll put this in parentheses. You don't need to write this part. This is just like how I would solve this with inscribed angle. according to inscribed angle theorem, I would say the following. The measurement of angle C, my marker's fading, is going to be 1/2 of its intercepted arc, just to relate this to the front clip of this section, to arc AB. And because AB is 180 degrees, because this is a diameter, that's going to force measurement of angle C to be 90. But because of the inscribed right triangle theorem, the fact that AB here is a diameter, that it passes through the center of the circle at Q, I can actually jump immediately to this. Measurement of angle C is going to equal 90 degrees. It just comes from this inscribed angle theorem up at the top. So I can jump immediately to this, which makes things pretty simple because now I just have to plug in the algebraic phrase they give me here for angle C. So instead of angle C, I would call it 2x degrees. Just substituting there for angle C. It still has to equal 90. And so to solve for the variable, I would simply have to divide both sides by 2 in this case, and x comes out to 45 degrees. Done. Just to prepare you the different ways you might see this presented, they might give you this situation where I have a right triangle inscribed in a circle, and maybe they give me the lengths of the chords that are created, and maybe I have to solve for one of the missing chords. Because it's a right triangle, I can apply Pythagorean theorem. So that's another way they could ask the question. All right. Maybe they give me one of the angle measurements, like say they tell me that angle B here was 30 degrees. Well, because it's a right triangle that forces angle C here to be 90, I can use that to figure out the measurement of angle A. And maybe they ask me like, all right, find arc BC. Well, arc BC is the intercepted arc for angle A. And so that might be another way where they're like, hey, angle B is 30 degrees. I could use that to figure out what's left over on the inside of the triangle, because that's 90. That would force this to be 60. And since this inscribed angle 60 is 1/2 of its intercepted arc, I could multiply it by 2 to find the measurement of arc BC. All of those are just different ways they can ask you those kinds of questions, all stemming from the fact that because it's a right triangle inscribed in the circle, that forces this angle here to be 90 degrees. All right, this one was a little bit simpler than those other ones I described. All right, example B. Last example for section 4. We're given a circle again with the following quadrilateral or four-sided figure drawn on the inside. So the fact that I'm going to get a four-sided figure on the inside, whether it's a square, rectangle, or whatever, because it's a quadrilateral, that means that opposite or diagonal angles in this figure are going to have to be supplementary. So whatever this angle measures here, it's going to have to add to make 180 with whatever's down here. Okay? And they'd give us the following letters. They could name it anything, but we get D, E, F, G. And then they tell us the following. We're given a couple of variables, a couple of unknowns. We're told that angle G here is some unknown y degrees. We're told that angle D is some unknown z degrees. I know my z's look a little bit like the number 2. That's why I put this little dash mark in the middle right there, just so that you know when I write it what it means. And then the other two angles, they actually tell us explicitly what they measure. They tell us that angle E is 120 and that angle F is 80. For the record, they could have given us entire algebraic phrases here. Like they could have said 2y minus 17. They could have said 8z plus 45. Okay, they could have done any number of things here. They told us explicit numbers. It makes the math a little bit simpler. But here is essentially what I can do with the inscribed quadrilateral theorem. Because angles that are opposite each other need to be supplementary, the following has to be true. The measurement of angle D plus the measurement of angle F, angles that are opposite each other, has to be 180. I'll give myself a little bit of space just so I can say the other one. Measurement of angle G plus its opposite, measurement of angle E, must also be 180. At this point, I'm just substituting for what I know and solving for the pieces I don't. So let me just do that really quickly. Z plus 80 equals 180. I would simply subtract 80 from both sides, and I get Z is 100. Done. G is Y, and E is 120.